Walk with me through the Whit and Whit book, Chapter 9, Sampling Distribution of the Mean. Let me just tell you up front, some of this is not going to make sense to some of you. Maybe none of it will make sense to any of you. That's okay. But I need to show you a couple things to let you know why we're going to do and why we can do things we're going to do a little bit down the road. Uh, I love this. I always love their definitions. On page 194, what is a sampling distribution? The sampling distribution of the mean refers to the probability distribution of means for all possible random samples of a given size from some population. Any questions about that at all? Is that clear? All right, let me springboard off. Yeah, exactly. Maybe thick mud too. Let me springboard off the example I used a little earlier about that. I said if you've got 30 people in the room, there's a pretty fair chance, about a 2/3 chance that some two people are going to have the same birthday in terms of just days and months. October 25th or whatever. That's because if I'm taking a sample size of 2, which is in reality not practical, but theoretically it works for me. How many sample sizes, how many pairs, possible pairs do I have? And we said the answer is a bunch. So, the sampling distribution of the means in semi-plain language is all the possible ways you could get samples of a given size. You don't write this down, it doesn't matter, I'm just going to show you some things. For example, if I have, let's say I have a population of 10,000, and I'm going to take a sample size of 100. How many ways could I have that 100? How many different possibilities could I have of that sample of 100? And the answer is not just a bunch, it's a bunch, a lot. Here's what it means. And again, I'm going to use very, very, very small, unrealistic numbers, but it shows you what we have here. All right, let's say I have a population of a distribution of these numbers. Let me get the screen set up the way I want it set up. Or maybe I want it set up. We'll find out. All right, here's my population. And I'm just going to let numbers be my population. My population is the numbers 2, 3, how many words is that all I want to do? Yeah, 2, 3, 4, and 5. So my population size is 4. And I want to take a sample size N of 2. So I'm going to pick 2 out. I'm going to do this called statistically in probability, which sometimes we talk about with replacement. I'm going to do this with replacement because you'll see what I mean in a minute. That means I could get, and I think I'm going to type this because I can't write this small. Let's get up here. I could get a 2 and a 2. I could get a 2 and a 3. I could get a 2 and a 4. I can get a 2 and a 5. I can get a 3 and a 2. Now, does it matter if that's the same thing as a 2 and a 3? It does in this case. I just get a 3 and a 2. I could get a 3 and a 3. I could get a 3 and a 4. Oops, oh no. I could get a 3 and a 5. Did it again. I could get a 4 and a 2. I could get a 4 and you see the pattern, I'm guessing. 4 and a 3. I could get a 4 and a 4. I could get a 4 and a 5. I can get a, take a breath, space here. I can get a 5 and a 2, a 5 and a 3, a 5 and a 4, and I could, oops, it's 5 I said. And I could get a 5 and a 5. How many is that? 16, so it should be 16. So I've got 16 ways I can get that sample size of 2 with replacement, not worried about the order, that sort of thing. Okay. If I get a 2 and a 2, what is my mean? This is not rocket surgery either. If I get a 2, what's the mean of 2 and 2? 2, yes, okay. It really, I mean, this is a doctoral level class. Okay. Oops. Yeah, they're numbers. Sorry. No, they're yeah. What's the mean of 2 and 3? 2.5. All right. The mean of 2 and 4 is going to be a 3. The mean of 2 and 5 is going to be a 3.5. Is that right? The mean of 3 and 2 is going to be 2.5. The mean of 3 and 3 is going to be 3. The mean of 3 and 4 is going to be 3.5. The mean of 3 and 5 is going to be 4. Mean of 4 and 2 is going to be 3. Mean of 4 and 3 is going to be 3.5. Mean of 4 and 4 is 4. Mean of 4 and 5 is 4.5. Mean of 5 and 2 is 3.5. Tell me when I'm wrong. Mean of 3 and 5 is 4. Mean of 4 and 5 and 4 is 4.5. And mean of 5 and 5 is a 5. So I've got 16 means, but they're not 16 different means. Some of them show up more than one time. So there are 16 things that are equally likely to happen. See how we're building on probability. They're equally likely to happen. Just like theoretically, there's equal chance of selection and assignment for a purely, truly randomized sample. Okay, how many out of the 16 possible outcomes, how many of those ways give me a 2? Just one of them. So 1 out of 16. There's a 1 out of 16 chance I'm going to get a 2. What's my chance of getting a 2.5? Is there another? There's 2 of them. So there's a 2 out of, I'm going to stick with the 16s, 2 out of 16 chance of getting a 2.5. Actually, let me do this a little bit differently. Just a little bit differently. If I look at these 16 outcomes, I get these 16 means, but again, they're not different means. So what are the, of all the possible means I can get a 2, I can get a mean of 2.5, yeah, I'll do it this way, a mean of 3, a mean of 3.5, a mean of 4, one of 4.5, and one of 5. So I can get 1, 2, 3, 4, 5, 6, 7 possible means. Some of them I'm more likely to get than others. So how many of those out of 16, how many of those are 2s? Just 1. So 1 out of 16. And we said how many of those are 2.5s? 2 out of 16. 3s, there are 3 of them. 3 out of 16. And there are 4 ways to get a 3.5, so 4 out of 16, which is a 1/4 chance. 3 out of 16. We're going to notice some symmetry now. There are 2 ways to get a 4.5. 2 out of 16 ways, and only 1 out of 16 ways to get a mean of 5. Okay. Now, my initial population, 2, 3, 4, and 5. Do you see any pattern to that, other than they're just kind of sequential? If you were to graph those, there's only 4 points. You're not going to get much of a graph out of that. But let's graph these. Let's look at these. I'm going to go from 2, 2.5, 3, 3.5, 4, 4.5, and 5. How many ways can I get a 2? A 1. Just one way. How many ways can I get 2.5? One way. 3, 3 ways. 3.5, 4 ways. 4, back to 3. 4.5, 2. 5 is a 1. It looks like a kind of a, one of the, but actually, actually think of it kind of this way. It's a bell curve. It's a normal curve. Here's the magic. Tell me when you're impressed. I'll wait. Here's the magic. When we take all the ways you can get a sample size, and we graph the likelihood of those outcomes, we are always going to get a normal curve. Even if the initial distribution is not normal. It's not a bell curve. When you take the mean of the means, the mean of all sample means, and you graph it, you get a normal curve. Now, you saw me do it, but your question is still kind of, well, gee, that's a nice, neat part of the trick. So what? Here's the so what. You remember those things we knew about normal curves, the 68%, the 95%, the 99%, and all that stuff? That means that regardless of an initial distribution, certain things we want to do with it, certain things we want to find out, certain things we want to test, we can use what we know about normal curves to make those tests. So some statistical procedures, even though they deal with distributions that are not normally distributed, we can still use what we know about the normal curve in those questions, those kind of comparisons. This is called, whenever something's based on a normal curve, whether it's normal or not distribution, that's called parametric statistics. Parametric means what you're doing is based on the normal curve. I don't care if you got your stuff normal. For example, some skewed distributions we talk about, let's say classroom test scores, those are typically not normally distributed, but when you want to make certain comparisons, we'll use some of our characteristics of the normal curve to do that. Now this is a little bit of a sneak preview into the second half of the chapter, actually the end of the first half of the chapter. We're going to not get too far away from this. Look at a couple more things and walk them through, and I'll come back to this again in a minute. Make the point again. A couple things the rest of the chapter. The top of page 199, You've got some symbols, most of which we've already seen. The mean can be noted by X bar if it's for a sample. It's denoted by mu, X bar, mu, kind of a curlicue little under lowercase u, or the sampling mean of the distribution, which again we're not going to use. I don't know that we'll ever use the symbol necessarily, but they just tell you that that is that mu sub X bar. We know that standard deviation is S for population, lowercase sigma for sample. I'm sorry, I got that backwards. S for sample, lowercase sigma for population, and if you want to talk about the standard deviation of the or the standard error of the mean, I'll talk about standard error in a minute. That's going to be important. U sub X bar. This one we will use. This one we will. That is the symbol for what we're going to talk about as standard error. And that's kind of my next topic. So understanding that we can use this normal curve stuff, and let me come full circle and tie back around to what we mean. In the normal curve, what is the mean? In the middle, which is, what's the number here? Where on this scale is the mean? Right here, 3.5. This is the magic in it. What's the mean of my initial population? 2 plus 3 plus 4 plus 5 divided by 4 of them? 3.5. When you take all the possible sample combinations and weight them according to where they'd follow the normal curve, the middle one, the mean is going to be the mean of the population. So this has to do with the likelihood that our sample is going to look like our population. If you have 100 scores and you draw a sample of 10, is it possible that you're going to get the 10 highest scores? It's possible, not very likely. Usually they're going to be spread out. The larger your sample is, the more likely they're going to be spread out like the population is spread out. So sample size means something, but beyond a certain number, it's more important how you get the sample, that you really randomly sample. And we're going to, sometimes we pretend we can randomly sample. We know we just can't. But the full circle part is that the mean of the population, which usually we don't have the population. Usually we don't know the population mean. Sometimes you do. I'll give some examples where we do. But the mean of that, if you want to sample and come up with what the mean of the population probably is, we can do it by fairly small samples sometimes. But there are a lot of ways we can get those fairly small samples. So the mean here for all of our samples together is the same as the mean for our population. If you had that population of 1 million and you're selecting a sample of 1,000, there's a lot of ways you can get that 1,000. You can't even list them all. I just pick a population size of 4, and there were 16 possibilities of that. If you add a 5th one in there, the number's going to grow exponentially. So you can't count these. You can't list them all. But we can list some very small, artificially small ones to show you how the model works, or to show you why what we're going to do works the way it does. Okay. I don't really want to ask if that makes sense. I just want to ask if you follow me okay. If you follow me okay, I'm good. If you could do it and explain to somebody else, you probably can't, and that's okay. But this does get us into something else that is important we need to understand. And that is called, I told you what the next thing that would be on this is called standard error. Standard error. How often does the data we get from some sample we take, how often is that inaccurate? Not a trick question, but a loaded one. The answer is not even it depends. How often does your sample information deviate from what's true for the population, let's say? And the answer is pretty much all the time. Pretty much all the time. The question is, are you close enough to draw any conclusions from it, or do you have reason to think you're close enough that you can make some reasonable claims? Let me put the scenario this way. Have you ever taken a test and made worse than you really deserved or worse than you really knew? It's rhetorical because the answer is yes. Why is that? What are some reasons you make worse on a test than you really should have made? That test is not an accurate measure of your knowledge. All kinds of things. Can you be less specific? Okay. Yeah, maybe okay, you're having a bad day. You're having a bad day, that affects performance. So that would cause you to make less than you really deserved. And that's just one of, again, all kinds of things, as you say. We could come up with a bunch of them. Yeah, okay, you didn't study the right things. I'll save that phrase for in a minute. But, yeah, there are a lot of reasons you can make worse on a test than you really deserve. Have you ever taken a test where you made better than you really deserved? I mean, how do you think I got through school? Yeah, and what are some reasons for that? You what? Well, if you did know, wouldn't you deserve to make pretty good on that? Maybe you cheated. Yeah. Okay. Maybe you cheated, and that test score did not accurately reflect what you knew because you cheated. That's a possible reason that you would err on the high side. Maybe you got lucky. You guessed some things right, and that made you that showed you made higher than you really should have. If you guessed wrong, you didn't know, so it should be wrong. So usually that kind of error is going to be on the top end of things. So a lot of reasons we don't make what is accurate for us to make. Oops, where am I going? Okay, so that's what I mean by error. Error is when something is not accurate. The example I gave was you don't make on the test what you really should have made. Now, is it fair to you that you're in my class, and let's be real unimaginative. I'm just gonna grade your performance by test. Let's say we know better than that, but let's say I bet if I just give you a test, and that's going to be your grade for the semester. You're not happy with that, are you? Oh, you must love tests. You want to take more? Well, if you take that one test, you might have gotten lucky and gotten higher than you deserved, or I might have missed marking some things wrong. Could be greater error. Can work on either side. Either you give too much credit or not enough credit. Don't you want to take the chance of getting lucky and really having maybe you got a shot at it? I see 2 nods and don't see agreement from off campus. I see anybody. There it is. Okay. So one test is not an accurate, or probably, or there's more chance that one measurement is going to be inaccurate. But if I take more than one, what if if you have 5 tests? There's going to be some error in each test. But isn't it more likely that sometimes you're going to get error on the high side, and sometimes you're going to get error on the low side, and that error is going to kind of cancel itself out? It's exactly the same reason that we don't have an N of 1. You select more than one thing to measure, to look at. The more you look at, the better your information is. Again, after a point, it kind of levels off. It's not better. It's better to take 5 tests than 1 test. It's probably not better to take 100 tests than 1 test. You get to the point where it does. You get to the point where it can be counterproductive, which is, what people would say about our school system now. That's what we do. We don't teach, we test. I don't know what you're going to test if you don't teach, but that's what we do. So, the point is about error is that Yes, there's error every time we measure. But the more we measure, the less overall error there tends to be. Error tends to, as you said, balance out. Now here's something else we know about error. You know, sometimes you err on the high side, sometimes you err on the low side. Overall, if we're measuring error, it looks like this. Error tends to be normally distributed. If here's our mean, yeah, I'm going to get a little error high or low. And the further out, it's less likely I've got error that's got to be here. Even less likely I've got to get this much error. So error tends to hover around the mean. Tends to cancel itself out. Here's the way we calculate error. Page 200. Told you we'd use this symbol. Lowercase sigma sub x bar means standard error of the mean. It's our measurement of error. Here's how much error is likely to be in some measurement. Has to do with two things. Has to do with this. Remember from 3 minutes ago what we said that is? Maybe 8 minutes ago now. Has to do with the standard deviation divided by the square root of n, our sample size. So error is based on two things. Standard deviation, spread outedness, and sample size. Now, how does sample size, look at the formula, how does sample size affect error? If n increases, what does that do to the error after we do the calculation on our slide rule with this little formula? If n increases, that means it's a bigger number. The square root of it's going to be a bigger number. We're dividing a bigger number into some other number. When you have a bigger number in the denominator, don't you get a smaller quotient? So the larger the sample size, the smaller the error. Which is kind of what we've seen all along. That's exactly what we've seen all along. The larger the sample size, the smaller the error. Conversely, the smaller the diameter, that's our numerator, the diameter, the standard deviation, that too. The smaller the standard deviation as a numerator, the smaller the number you get when you divide by something. The larger n, smaller error, smaller standard deviation, smaller error. If something's not that spread out to begin with, you're probably not going to be that far off target anyway. Okay, let's look at a couple examples. Here's I like this one too. I don't really need to read, but it does come into place. Something called this. If my standard deviation is really wide, there's a lot of room for error. If my standard deviation is really small, there's not as much room for error. And I think you can see it on the screen. Yeah. So the larger standard deviation, the bigger the error. Smaller standard deviation, the smaller the error. Okay. We're talking about something called the central limit theorem. Don't write this down. It's not going to be on the test. It's one of those definitions I just get amused by reading. The central limit theorem, I'm reading on page 202, right almost down to the middle. The central limit theorem states that regardless of the shape of the population, the shape of the sampling distribution of the mean approximates a normal curve if the sample size is sufficiently large. That means when I put all those together, I got a normal curve. And bigger is generally better, sufficiently large. So you want to have a large enough of an n. But after a certain point, it doesn't much matter. It depends. The question is, what's a certain point? It depends. It depends on not necessarily population size. It depends on sample size and sample selection. It means that with the example we used, did I save that? I think I did. Yeah, with the example we used, my pattern went more like that. I just kind of superimposed a normal curve on top of it. I really didn't connect the dots to get the curve. But if I had more more of an N, it would start to curve along like my curve did. It just kind of went straight up from lower left, upper right, and then from that point to the lower right. So it didn't approximate a curve very well, but it pretty much fit on the curve. If I had a larger sample size and both larger population and sample size, and if I could possibly list all that, so I would get something that would look, it would look almost like a continuous normal curve. I really didn't have sufficiently large sample size to do it with this. And I don't want to do one that has sufficiently large sample size. Nobody does. Okay. Let's just do a couple of quick things. Let's say, for example, let's look at the SAT. Let's look at the ACT again. ACT. And we said the ACT has a mean of 21. Yeah, come on, Don. And a standard deviation of 4.5. Let's say you have 100 students in your district who take the ACT, or 100 students in your school who take the ACT. So your N is 100. What is your standard error? Oops, I put my decimal in the wrong place. Okay, your standard error is 0.045. Now what we could do with that, I think I have room to, is I could take my normal distribution and I could go, remember how it would go at 1, 2, 3 standard deviations? -1, -2, and -3 standard deviations. I can likewise do that with standard errors. So one standard error above would be 0.045. One standard error above would be 0.045. Two standard errors above would be 0.9 or 0.09, and so forth. Remember, our standard error is less than our standard deviation because we're dividing by a number. But I can go out +1, +2, and +3 standard errors, and we'll see examples of that a little later. Just like I can go out 1, 2, and 3 standard deviations from the mean. Okay. Questions, thoughts, comments? Okay, you've got your homework assignments that we'll go over with the next video. And if there are no questions, we'll stop the standard error stuff here. And we'll all this stuff, we'll bring it together. It'll come full circle, and you can kind of see how it works together. Don't get too bit out of shape about standard error, the mean, and how many ways you can get a sample size. The idea is that this is a theoretical kind of thing to where, in theory, here's why we can use this normal curve stuff. That's all I'm saying. The question was, ACT had a mean of 21. How do I know it's 4.5? Because we know the standard deviation, and we use this in other examples, that the standard deviation of the ACT is about 4.5. If you take all the people who've taken the ACT, the mean stays real close. It changes a little bit year to year, but it stays real close to 21. And the standard deviation changes just a little bit, but stays real close to 4. We just know that. Kind of like we know the mean and standard deviation for the SAT and some other examples we've used. Okay.